Hi. So this lesson continues our study of thermodynamics, the flow of energy into and out of chemical reactions. So to start with, we'll do a quick summary of what we learned yesterday. If you're observing a chemical reaction and the temperature goes up, or if the temperature feels warm to you, that means it's exothermic, because if it feels warm, that means energy is coming out of the reaction and going into your hand. And then conversely, if the temperature goes down and it feels cold to you, that means that you are losing energy and it's going into the reaction. So that's endothermic. So I think that's a nice shortcut way of remembering which is which. That helps me out. So today, we're going to finally answer the question, okay, where does the energy that comes out, where does it come from? When the energy goes in, where does it go? So like in this burning reaction, you burn wood and tons of energy comes out, but where is it coming from? People say it's coming from the chemicals that's in the reaction. And then, you know, the question is, okay, but where is the energy in the chemicals? Like obviously they have energy stored inside of them, but where? And why do some reactions, the energy comes out, but other reactions, the energy goes in? So to understand this, we need to remember that there's two kinds of energy at play here. So the first kind of energy we've already learned about earlier in the year, kinetic energy is the energy of motion. So when you measure the temperature of something, that's the average kinetic energy of the particles. So higher temperature particles have more kinetic energy because they're moving faster. The other kind of energy is potential energy. And potential energy, a way to think about it is stored energy, energy that has the potential to make motion happen later. So the question is, where is the energy stored in a chemical? Well, there's not a lot of options. Like there's just some atoms and some bonds holding them together. And it turns out where energy is stored is in the bonds between atoms. If you imagine this hand is an atom, this hand is an atom, then this rubber band is the bond between them. And this rubber band, we can have a high energy bond where we stretch the rubber band out, there's lots of energy in this rubber band, or we could have a low energy bond where it's not stretched out very much. So this is how we can imagine the bonds holding atoms together. We have low energy bonds, we have high energy bonds, and just like a rubber band, the more you stretch out the rubber band, the more energy is stored inside. This rubber band has a lot of potential energy. If I were to let it go, then all that potential energy would get converted into kinetic energy and it would fly super fast the more I stretch it out. Okay, so we can use this rubber band analogy to understand what's going on in a chemical reaction. So in a chemical reaction, anytime you want to break a rubber band, every time you need to break a bond, the chemical needs to absorb energy. So anytime you see any kind of bonds breaking, there's always a chemical, like in this case, H2, a hydrogen molecule. You need to add energy to break them apart into two separate hydrogens. So if I wanted to break this rubber band, you can imagine I have to put in a lot of energy. I'm going to do it. It's going to hurt. Ow. I'll show you the red spot on my hand later. But it takes energy to break bonds. Meaning the chemical breaking bonds is endothermic. If you want to make new bonds, then the opposite is true. That's exothermic. So instead of adding energy, they actually lose energy. And so one thing chemists don't like to do in their chemical equations, they don't like to have minus signs. So like if this first example here, the hydrogen gains energy to break the bonds, they put the plus energy on the left, that makes sense. And so then what would make sense would be, why don't we just say two hydrogens minus energy for losing energy? but since they don't like to have minus energy, they moved it over to the right-hand side and just put it as plus energy on the right. So, summarize this slide. Breaking bonds, you absorb energy. Forming new bonds releases energy because the atoms are becoming more stable. Okay, so the last thing for today, this is the most useful tool for understanding the flow of energy, for visualizing the flow of energy in a chemical equation. Chemists use what's called a potential energy diagram. It basically shows how much stored energy is in the chemicals at different points during the reaction. So on the x-axis, we have time, or sometimes it's just called the reaction progress. So we have the beginning of the reaction, we have the middle of the reaction, and we have the end of the reaction. And the y-axis just shows potential energy, how much energy is stored inside the chemical. So if the reaction is endothermic, that means energy is going in to the chemicals. That means that the chemicals we start with have a lower potential energy, and the products of the reaction at the end that just gained all that energy would have more energy. So on a potential energy diagram, that's endothermic. The reactants start with less energy, but then as energy flows in, they gain energy. This would be like the vinegar and baking soda. That's an endothermic, it's absorbing energy. So the products have more energy than the reactants. So the question is, what happens in between? Does the energy just gradually, steadily increase? And the answer is no, and it has to do with what we learned about last week, or a couple weeks ago, with this idea of effective collisions. For baking soda and vinegar to react, the particles need to collide together, and the reason why they're colliding is that you need to break the old bonds apart. So before the vinegar and baking soda can react to release the bubbles, you have to break the bonds, and that takes energy. So in the middle of the diagram, the energy goes up, 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 and it actually takes quite a bit of energy. Uh-oh. Yeah, okay, it worked. This represents old bonds breaking. And then, right after the old bonds break, you make new bonds. And as we saw before, the new bond, making a new bond, releases energy because they're more stable. So the overall shape looks something like this, where there's a hump in the middle. And the thing is, every single chemical reaction is going to have a hump, because in every single chemical reaction, you need to break the old bonds before you can make the new bonds. So this represents, as you go up this hill, the bond has more and more energy stored in it, more and more energy stored in it, energy is flowing into the reaction. You get to the very top, the bond breaks, and then new bonds start to form, and finally you end up with the products. So that's an endothermic reaction. Finally, for an exothermic reaction, similar idea, but instead of gaining energy, the reactants are losing energy. So instead of starting with the reactants at a low energy, they actually have more energy, and the products, since it's losing energy, the products will end up with less energy. So our reactants are up here, our products are down here, and what happens in the middle? Well, it's still a chemical reaction. The particles still have to collide with enough energy to break the old bonds. So there's still going to be a hump where we break the old bonds. It's just that in an exothermic reaction, the new bonds have such a low energy that the energy that's released is huge compared to an endothermic. So we still have going up where we're breaking the old bonds and going down where we're making new bonds. And so the real difference between an endothermic and an exothermic reaction is in this exothermic reaction, when we make the new bonds, those bonds are so stable, they release so much energy that overall the whole reaction loses energy. In an endothermic reaction, we start with lower energy bonds and we end with higher energy bonds. So it takes more energy to break the old bonds than it does to make the new ones. So that is an overview of potential energy and potential energy diagrams. And they may seem a little weird at first, but the more you get used to them, the more they help in picturing and understanding the flow. We'll be practicing more with these next week. Have a good day.